This is a presentation that I gave at the Midwest Relativity Meeting and sort of has my thoughts on extending the work that we're doing on field theory, general relativity, and what it would mean for quantum gravity. So let's go through them real quick. The idea is that we want to generalize a series of results that we have to for classical mechanics, and we want to generalize them to field theory. So let's review a little bit what these results are. What we have found is that Hamiltonian mechanics is exactly the deterministic and reversible evolution of finitely many independent degrees of freedom. So if these are Hamilton's equations, we can rewrite them in a more generalized way. Instead of writing position and momentum, we write these C variables that span both position and momentum. And so we have that the derivative in time of the position of momentum multiplied by this omega AB, which we can think it as essentially as a big matrix that changes the Q into P and the P into minus Q. This matrix applied to the displacement field gives you the essentially the gradient of a Hamiltonian. And so you can write this as lower a as essentially the displacement field, which we can also call SA, contracted with the symplectic form, and this it's basically the displacement field where things are going in phase space rotated 90 degrees in position and momentum. So this is a more compact way to represent this equation, and it sort of geometrically tells you a little bit more what's happening. Another way to characterize this equation is to look at the evolution of this omega AB, this matrix, this symplectic form. And what you find is that if you have a generic field, this form, the sort of the infinitesimal time step is the original form, and the first order term is essentially the curl, the exterior derivative of the displacement field SA. So now we have found really a geometrical interpretation of what the action is. The action is the line integral of the vector potential of the flow of states. And since it's the integral of vector potential, it's unphysical. The value of the action is actually not a physical thing that we can go and measure because it depends on the arbitrary gauge that we chose for the vector potential. But the variation of the action, that's actually physical, because what's happening when we are doing a variation of the action, we are actually calculating the line integral of the vector potential over the closed curve made by the path and its variation. And by Stokes' theorem, that's basically calculating the flow of the field within that sliver of the extended phase space. And that's going to be gauge independent because that's a function of the flow, and that's physical. So now we have that the flow is going to be zero for any variation if the path is an actual trajectory, because if the path is an actual trajectory, then the flow is always tangent to that trajectory, and therefore if you take any surface that it's with a small variation of that path, there is not going to be any flows that go through. The flows that go through is zero, and therefore the variation of the action is always zero. So the point is that I have other videos if you guys want to go and look at this in more detail, but the point is that everything can be understood very simply, very geometrically based on this correspondence between the math and the physics. And everything in classical Hamiltonian mechanics and classical Lagrangian mechanics can be understood very, very nicely in these terms. And so what we want is understand how this works and how to extend it for field theory. So to recap, let's understand how we count states and configuration. If you are in the discrete case, then if you're counting the configuration, you just have the set of possible configuration and you just count them with a counting measure, 1, 2, 3. Same thing for the states, and same things for the degrees of freedom. You have 1 and 2 degrees of freedom, that's what you count. Now, if we are in the continuous case now, we have, for the configuration, we have a surface made of, let's say, position and momentum. And so where we get the number of configuration is by integrating this omega AB along the surface. And so this omega AB, this symplectic form, is actually telling us the configuration density. How many configurations do we have per unit of surface? If we want to get the states, then we can get the volume form from the symplectic form, and we're going to do a volume integral, and we're going to get a number. And again, the important thing is that we're not counting the points in the volume to get the number of states, because that would be infinite. What we do is actually integrating the volume form, which gives us a state per volume density. But for the number of degree of freedom, we're still counting them. We have finitely many, and we count them 1, 2, 3, X, Y, Z. Those are the degrees of freedom that we have. So now if we imagine that we want to extend all this reasoning to field theory, well, now the degrees of freedom themselves are on a continuum. They are not discrete. And so we are not going to be able to count the degrees of freedom with a counting measure. And so we need something else. We need some kind of density to do that. And that's basically the idea. What the conjecture is that field theory in general relativity is really the deterministic and reversible motion of independent degree of freedom when we have infinitely many. We have a continuum of degrees of freedom. So in the mechanics case, in the finite degrees of freedom case, we saw that the Lagrangian, the variation of the action, is actually some flow of states. And on field theory, we have still we have an action, but we have a Lagrangian density. So it's the integral of a Lagrangian density. And the question is whether this line integral is basically a vector potential or the flow of state density. That's why we have a Lagrangian density, because we have a configuration density. We have number of configuration per degrees of freedom. We need this quantity, and the question is, how do we get it? What is the correct formula for that? And another thing that we need to understand is how do we count the number of degrees of freedom? And here, very likely, it's going to be the volume of space, not space-time, but really space. Because if we imagine that we have a volume of space and we double the volume, we expect that we have to specify twice as many initial conditions, twice as many configurations, therefore twice as many degrees of freedom. And one thing that what we know is, for example, that the Lagrangian density in general relativity is made of two parts. One that is the Lagrangian from the field, the matter part of the Lagrangian, and then we have the other part of the Lagrangian that has to do with the metric tensor. And so the question is, the conjecture is whether the matter part is really for the flow of configuration for degrees of freedom, because the fields represent the degrees of freedom, and the other part of the action is the flow of the degree of freedom themselves. Because the idea is that at the end of the day, we're going to have a Cauchy surface with all the degrees of freedom and the values of the fields at each point. And then we are going to evolve the Cauchy surface somewhere else. And we need to map two things, right? We need, yes, to map the value of the field from here to here. But you see, if let's say the space expands, well, if space expands, then that same degrees of freedom gets expanded into a broader region, so the number of degrees of freedom per volume sort of decreases, and since the total number of states need to remain constant, well, you're also spreading configurations into a different into a set of degrees of freedom. So this might be the thing that we need to understand geometrically, and maybe if we understand all of that geometrically, then again, the field theory equations sort of come out naturally from the assumptions, in the same way that Lagrangian mechanics and massive particles and their scalar potential come out essentially from the assumption in just classical mechanics. So that's what I'm trying to understand for field theory. And then, of course, how does quantum mechanics fit in all of this? Well, there is a problem actually with what we just said, the idea of counting on a continuum, because so imagine that we have a volume in phase space, and you say, okay, this volume in phase space represents 3 states. Very good. You divide that volume in half, and now there's going to be half as many states, and so you're going to have 1.5 states, which again, maybe that's okay. But if you divide it again, you're going to have something like 0.75 states. So you have a region of states that contain less than 1 state. And that does not quite make sense. It does also not make sense because if you have a uniform distribution, the entropy is the logarithm of the count of states, and therefore if you have less than 1 state, we have a logarithm of a number less than 1, you have a negative number, and so that would mean that you have negative entropy, which is also does not make much sense. The problem of counting on the continuum is the following. We would like to have these three requirements satisfied. First, we would like to say that every state is a single case and therefore it has to count as 1. Then we would like to say that any finite continuous range carries finite information, carries finitely many states, and therefore you want a finite continuous range U to have a finite measure. And then you would like to have the count additive for disjoint set. If you have 2 sets that are disjoint, that have nothing in common, then the total number of states is the states that are here plus the states that are here. And the problem is that these are incompatible because a finite continuous range has infinitely many points. And so if you say I want to have that every point, every state counts as 1, and I want to be additive, then if I have infinitely point, I have an infinite set. So this do not work. What you can do is pick 2 of these 3 elements and discard 1. So if you discard the first one, you have a Lebesgue measure, the points count to 0, and you have that the measure, the number of states is the volume or the area of the region. This is what we have in classical mechanics. You can discard 2, and so you're going to have a counting measure, and this is what you have on discrete systems. Or you can discard 3, you can basically say, well, I don't care about additivity, and then what you get is essentially what happens in quantum mechanics. In quantum mechanics, you can define an analog of counting states by basically taking a set of states, calculating all the possible statistical mixtures that you can make on those states, calculating the entropy on all of those, taking the highest one, and taking the exponential of that. And that is going to give you a measure that, if you did the same thing in classical mechanics, would recover the Lebesgue measure and the counting measure. You would get the same thing. And in quantum mechanics, you get something similar, something that, for example, recovers the dimension of the vector space, but it's not going to be additive. It's going to be subadditive. And the way that you can see it is that if you take a single point it's a pure state, and a pure state is going to have entropy 0, so 2 to the 0 is 1, so every states count as 1, which is good. Now if you take 2 orthogonal states, then you can get to the maximally mixed state, which is going to be entropy 1, so 2 to the 1 is 2, so if you have a set of 2 orthogonal states, then you get 2 states. And if you get anything else instead, the entropy, the maximum entropy that you can achieve is less than 1, and so you're going to have a measure that it's less than 2, and therefore the measure is going to be set additive. And so the idea is that if you have 2 orthogonal states, then the states are really different states because they are really defined at everything else being equal. You can have a same preparation with 2 different settings and reach those 2 states, or you can have a measurement, the same measurement apparatus with 2 different cases, and so those cases are defined at everything else being equal. But if you take 2 things that are not orthogonal, then they have to be defined in different contexts. They have to be produced with different preparations apparatuses and with different measurement apparatuses. So they are not defined at all as being equal, so they're different, but they're not really two distinct, fully distinct cases. Okay, so if you buy this and if you say, okay, this is what actually quantum mechanics is there to fix. It's the quantum mechanics is there to fix how do we count on the continuum, because we can't really, counting with just standard Lebesgue measure, Liouville measure does not work, because we're going to have areas that are smaller than 1. Then the conjecture is that we are going to have the same problems when we're trying to count degrees of freedom in a field theory. And so the conjecture is whether quantum gravity is really putting a lower bound on the count of degree of freedom in the same way that quantum mechanics puts a lower bound on the counts of configurations per degree of freedom on the count per state. And as I said, this is going to be exactly the same problem. We would like to every point in space for a field theory counts as a single degree of freedom. And when we have a finite volume, we want to have finitely many degrees of freedom. And we want, if we have two disjoint areas, that would, the degrees of freedom, the number of degrees of freedom sums. And again, this is not possible. And one of the reasons that quantum mechanics might be a little bit inconsistent with a field theory is really because you're trying to put a lower bound on the number of configuration, and you don't have a lower bound on the degrees of freedom. So once you say I have some number of configuration per degrees of freedom, you can make the number of degrees of freedom as small as you want, and therefore you're going to have configurations and states that are less than 1, which is what quantum mechanics was trying to fix. So I think that's why, sort of conceptually, quantum mechanics and field theory are incompatible, and we need to do something. Okay, so what we need to do, well, we are probably going to sacrifice the fact that the count is additive for this joint region in the same way that we sacrificed that the count was additive in phase space. And so if we have two distance points, right, distant point in space, then we would want to say that those are independent degrees of freedom that are really, I can set the value on one without interfering with the other, and so we will want the count to be additive if things are separated enough. But when they're close, then we are not going to expect those degrees of freedom to be independent, because you are below the Planck scale, and therefore you can't really set the value at one point independently from the value of the other point. And so if that's the idea, well, the kind of my point is that adding a lower bound on the state count required a severe revisitation of how you do particle mechanics, right? You have to go from classical mechanics to quantum mechanics, where the phase space now is severely different. You're in a projective space, you have the projective complex space, so you have some structure that is significantly different. And the question now is, well, if we have to do something like that for space-time, then probably we need another massive change in math, and we need to be a little bit more guided to get it, because it's probably not just going to be a simple another version of differential geometry in some sense. So, and I think I don't have an answer for how to do this, but I do really think that this makes a lot more sense. It's very, very well conceptually motivated. So, okay, so to wrap it up, classical Hamiltonian mechanics is exactly the deterministic and reversible mapping of configuration over infinitely many degrees of freedom, and we have this mapped. And now what we want is to show that general relativity and field theories are exactly the deterministic reversible mapping of configuration over infinitely many degrees of freedom on a continuum. And this is where I'm actually trying to look for people to help me. I need to find essentially a Hamiltonian way to look at field theory and general relativity that connects well to information theory, that gives me the correct entropy, and then that we can give me also the sort of the correct geometrical extension of a symplectic form and stuff like that. And And if any of you have ideas or knows people that can help me with this, I'd really be glad, because it would cut the time of figuring this out by a lot. Then we saw that quantum mechanics sets a lower bound on the state counts, because the entropy of a pure state cannot be less than 0, and pure states have to count as one state. That's sort of what quantum mechanics fixes. And then the question is, then is quantum gravity basically just setting a lower bound on the degrees of freedom, so that we can have states and even vacuum states with regions that have a count of configuration that it's less than 0. And the whole idea of all this also would be to generalize the principle of our geometrical and physical understanding of the action principle to field theory and to quantum mechanics and to quantum field theory. And so again, these are things that I am actively interested in understanding, and quite frankly, I have no idea how to do it. And so I thought this would be a good video to put here in the channel, where I try to find other people to help me with these ideas. Okay, so thank you for your time. If you do have questions, you can write them in the comments, and we'll see if we get something done. Thanks.